the arc length in rectangular coordinates. Suppose that we want to find the length of f of x from x equals a to x equals b. How could we do this? Well, in calculus, when we want to find a measure like length, area, volume, etc., we usually start with a simple geometric shape. Then we shrink that shape down to 0, and we sum all these little pieces together. So what kind of simple shape could we use? Well, a very simple shape is a line segment. So I could draw a few representative line segments here. And if I could find the length of each segment and add them together, I could get an approximation for the arc length, and if I shrunk these down really small, I would get the exact arc length. So let's just take a look at this first segment. I know that the bottom length of this right triangle that we form is delta x. That top length there is delta y. And then the length in question, which I'll call s, is the square root of delta x squared plus delta y squared. Which means that the total arc length from a to b, if I shrunk everything down really small, would be the square root of dx squared plus dy squared from x equals a to x equals b. Now this is a true statement. To find the arc length, we're summing very small line segments. The problem is, algebraically, this is the wrong format. Because we really need something like this. We need the integral of f of x dx. Or maybe f prime of x, or something along those lines. What we're going to do is we're going to manipulate this equation algebraically by doing the following. Let's factor a dx squared out of both of these terms, leaving us with 1 plus dy over dx squared times dx squared. Convince yourself that if we multiply the dx squared back through, that we would get where we started. Now, if I keep going, simplifying it a little bit more, we get the integral from a to b of what? 1 plus dy dx squared, which we usually write as f prime of x squared for whatever reason when we're doing arc length. And then back here we have dx squared square rooted, so we can bring that out as dx. And now we have a format that we can use, or at least one that looks familiar, for which we have formulas to use. So the arc length, I'm going to rewrite it again, just a little bit prettier, is the integral from a to b of 1 plus f prime of x squared dx. And let's use this to do an example. We're just going to do one simple example. It's very hard to find examples you can do by hand, just because of the complicated nature of this integrand. So we're going to find the length of f of x equals 2/3 x to the 3/2 on the interval x equals 1 to 4. When I'm doing these things, I know I got to use my arc length formula. I know that I need an f prime of x, so I'm going to start by finding that. I get f prime of x equals 2/3 times, now let's do the power rule, 3/2 x to the 1/2, which simplifies down to just the square root of x, or x to the 1/2. I really need f prime of x squared, So that's simply x. And then I can plug in to get my arc length, which is the integral from 1 to 4, because I gave that interval, of what? Well, root 1 plus f prime squared dx. This is technically a u sub, but we can do without a u sub because u is x plus 1 and du is dx. So we get u to the 1/2 integrated, which is u to the 3/2, or 1 plus x to the 3/2, divided by 3/2, so times 2/3, from 1 to 4. I will leave that constant alone for now, and then I'll plug in. I get 1 plus 4 to the 3/2 minus 1 plus 1 to the 3/2. And that's good enough. This is the arc length of my function on the interval from 1 to 4.